In this lesson, we will examine exactly where to find the functional group stretches for different functional groups in an IR spectrum. So I will be going back and forth between the chart on this slide and examples of spectra of different functional groups on the next 4 slides. So it will be a little choppier than normal, but this is really the only way I can show you what I want to show you. So starting at the top of the chart, at highest frequency, we have the stretches to hydrogen. Okay, so we have OHs, NHs, and CHs. So OHs show up in alcohols and carboxylic acids. And the OH stretch in an alcohol, well, in both of these functional groups, is broader than most other stretches are. In an alcohol, it's just broad. Okay, it's maybe 200, 300 wave numbers wide. In a carboxylic acid, it is incredibly broad. It is huge. It is about 1,000 wave numbers wide. The only way I can really show this to you is to show you examples. Okay, so here's an IR spectrum of an alcohol, and as you can see on the left here, there is that stretch, the broad peak between, I would say, 3,100 and 3,400. So that is a broad peak. But it definitely comes up, and you don't see much of anything going down as far as 2,500. The peaks at 2,800 to 3,000 are CH peaks, as we'll see in a few minutes, that are present in essentially every IR spectrum. Contrast this now to the spectrum of a carboxylic acid, where the broad OH stretch extends all the way from 2,400 to 3,500, a width of 1,100 wave numbers. This really broad OH stretch is characteristic of carboxylic acids, and it really can't be missed. Okay, then we have NH stretches. They're also in the same region that you would expect OH stretches to be. I didn't include an example of one, but NH stretches are much narrower and much weaker than OH stretches. Okay, they're in that region, but they're much tamer, and in some cases not even that easy to pick out. So now we get to the CH stretches, and as we'll see in a couple of minutes, the CH stretches exact frequency actually depends on the hybridization of the carbon to which the hydrogen is bound. But one that is actually quite characteristic is the alkyne. Okay, so here's the spectrum of an alkyne, and you see that strong stretch around 3,300. That's the stretch of the hydrogen bound to an sp hybridized carbon in the alkyne. Okay, alkenes and alkanes are a little slightly lower wave numbers. Then you get to the stretches of carbon-carbon and carbon-nitrogen triple bonds. Okay, so the functional groups present here are the alkyne carbon-carbon bond and the nitrile. They both show up in the same region of the spectrum. So if we go back to our IR spectrum of an alkyne, you can see the carbon-carbon triple bond stretch there around 2,200 wave numbers. Nitriles also have a stretch in the same place, so you can't necessarily tell just from an IR spectrum if you have an alkyne or a nitrile. If you have the peak up at 3,300, that is characteristic of an alkyne that has a hydrogen, but that peak could be missing in an alkyne that does not have a hydrogen bound to the alkyne carbon. There are other spectroscopic tests that you can do to determine whether you have an alkyne or a nitrile. Okay, then we get into the double bond region, and the most important peak in an IR spectrum in general is usually the carbonyl stretch, because carbonyl stretches in compounds that contain them are very intense. So let's look at the example of the IR spectrum of an aldehyde. And you can see that, so carbonyl stretches occur generally in the region of 1650 to 1800. And most of them are clustered very close together between 1710 and 1740. So you can see the big, strong stretch going all the way down to the bottom of the spectrum, the big, strong peak, that is, corresponding to the stretch of the carbon-oxygen double bond. That is, as I said, very characteristic. In aldehydes, ketones, esters is generally right there around 1720 or so. In amides, it is shifted to slightly lower wave numbers, tend to be in the 1650 to 1680 range rather than above 1700. So that's an important way to tell if you might have an amide. Now this is the spectrum of an aldehyde that also contains an aromatic ring. You can see the structure of the entire molecule indicated here, and that also shows us regions in which you have the stretches associated with carbon-carbon double bonds. So you can see indicated in this spectrum the peaks around 1600, 1500, and even getting down to 1450. All of those peaks are associated with the stretching of the carbon-carbon bonds in the ring. So carbon-carbon double bonds in alkenes are generally in the 1600 to 1700 range. In aromatic rings, you will often find more than one peak, one below 1600, one up in the 1650 range. But that's the place to look for the stretches associated with carbon-carbon double bonds. But note that they are not nearly as strong or intense or in your face as the carbonyl stretch for the carbon-oxygen double bond. So the carboxylic acid, going back and looking at this again, this one has both of the in-your-face stretches. It has the incredibly intense C double bond O stretch, and then the incredibly broad carboxylic acid OH stretch. Okay, so that's basically our catalog of the different functional group stretches. But as one last thought, as I alluded to earlier, the exact position of the CH stretch gives information about the hybridization of the carbon. So a CH stretch to an sp3 hybridized carbon occurs to the right of 3000, typically around 2900. The CH stretch to an sp2 hybridized carbon typically occurs around 3000 to 3100, so definitely to the left of 3000. And as we already looked at, the stretch between a hydrogen and an sp hybridized carbon occurs at 3300. So that's actually far away from the sp3s and the sp2s. And you can see some examples of spectra here just to show this phenomenon graphically. So you notice all three of these have peaks between 2900 and 3000. Because unless you have an incredibly simple molecule, if you have an alkene or an alkyne functional group present in your molecule, you probably have some regular, in other words, sp3 CH bonds in your molecule also. So you will see the peaks associated with the regular CH bonds between 2900 and 3000. So as I said, virtually every IR spectrum, if we go back and look at them, do they have peaks between 2900 and 3000? Yes. Aliphatic CH stretch. Do we have them here? Yes. Do we have them here? They're there. You can't see them because they're overwhelmed by the carboxylic acid, and we have them here in the alcohol also. So peaks between 2900 and 3000 are not very useful, but if you have an alkene or an alkyne, they will have an additional peak to the left of 3000 due to that particular CH stretch on the differently hybridized carbon atoms. Okay, so I have by no means gone over every detail of how to interpret an IR spectrum, nor do I intend to. For this introduction to IR spectroscopy, all I was trying to do was to show you the major functional group stretches, show you some pictures of spectra so you can actually see what they look like. So when you acquire spectra in lab, they will make some more sense to you. and to tell you which functional groups you need to be focusing on the most. We will now switch gears in the next lesson and begin to discuss mass spectrometry.